All right, we have learned what the arcsine function is and what the arccosine function is and what the arctangent function is, and we've even computed some examples of all of them. Here are some properties of them. Now, what you're really used to saying is, if you take a function and you compose it with its inverse function, you should just get out identity, and it doesn't matter which order you do this in. Now, this is true provided x is in the domain of whatever it has to start in. So in the first line here, x must be in the domain of f inverse, and here x must be in the domain of f, because if I wasn't in the domain of the first function I tried to compute, then I certainly can't try to do anything. Okay. So in this order, okay. Oh, and then of course, sorry, f inverse of x must be in the domain of f, and f of x must be in the domain of inverse of x. So let's see what happens, okay? If I try to compute the arcsine of the sine of x, do I get back out x? I do, but only in quadrants 4 and 1. In this order, however, the sine of the arcsine of x only works when x is between -1 and 1. And it's exactly for the reasons that are spelled out below. Okay? What is the domain of sine x? Big asterisk, okay? Because that's not the function we're actually inverting. We're inverting the restricted version of sine x. And what was its domain? The restricted version had domain -π/2 to π/2. Similarly, in this bottom line, what's the domain of arcsine? -1 to 1. So these identities only work when you're in the domain of the interior function. If you're looking at that sine function, it has to be the restricted one because that's the function we actually inverted. So find the exact value of each of the following. Okay, so arcsine of sine of π/8. So sine of π/8 is just some number. Let's call it y. So I'm now looking for the arcsine of y. Let's call it theta. So theta is an angle. It's between -π/2 and pi, because that's how arcsine works. And the sine of that angle must be, the sine of theta, right, must be y. But what's y? Y is equal to the sine of π/8. So I'm looking for an angle in quadrants 4 or 1 whose sine is the same as the sine of π/8. Well, π/8 is already in quadrant 1. So there, π/8 is an angle whose sine is the same as the sine of π/8. And I was already in the domain of that restricted sine function, because π/8 is indeed between -π/2 and +π/2, so no issue here. But in part B, okay, if I do the same argument, say, let's call the sine of 5π/8, let's call that y. Then the arcsine of y, I'll call theta. So theta is an angle. It's got to be in between plus or minus π/2. And the sine of this angle is the same as y, which is the same as the sine of 5π/8. That's how we define y. Now, I can't say that theta equals 5π/8. I can't say this because 5π/8, notice 5/8 is just a little bit bigger than 4/8. It's bigger than a half. So that angle is too big. Let's look at a picture. Okay, I'm going to clear off all of these pen marks, so pause and copy down what you want. Okay, I'm going to clear them off. We're looking for, we've done part A, by the way, this was just π/8. Let's look at a picture of the unit circle. Okay. What is the sine of 5π/8? I mark off an angle of 5π/8, which is just a little bit bigger than π/2. The sine of 5π/8 is this y coordinate. Now what I'm looking for is an angle in quadrant 1 or 2 with the same y coordinate. and this angle here. Okay, so this arcsine of this height will not be this angle because I have to be in quadrant 1 or 2. It will actually be this one right here. Okay, so I'm going to clear off my picture because the book's going to explain this using, you know, nice pre-typed stuff. Okay, so we already did part A, sorry. So there's part A again. So for part B, 5 pi over 8 is too big. Okay, so I can't just say the arcsine of sine of 5 pi over 8 is 5 pi over 8. So we have to find an angle in quadrants 4 or 1 whose sine has the same value. Okay, and again, 5 pi over 8 is in quadrant 2, but I need to be in quadrant 4 or 1. So the way we can figure out what angle that is using some symmetry arguments. So I'll expand their picture. They drew it a little small. Okay, so 5 pi over 8 is about here. What is going all the way around to this axis? That would be pi, aka 8 pi over 8. So here's 5 pi over 8. All the way to the negative x-axis is 8 pi over 8. So what's missing is 3 pi over 8. And so by a symmetry argument, that's what this angle here is going to be as well. So this angle here is 3 pi over 8, and it's going to go to the same height. So if I take the same height as 5 pi over 8, I put it into quadrant 1, the relevant angle is 3 pi over 8. And that is in quadrant 1 or 4, specifically it's in quadrant 1. So the arcsine of the sine of 5 pi over 8 is actually 3 pi over 8. So one way you can also view this is that as a number, the sine of 5 pi over 8 is equal to the sine of 3 pi over 8. And 3 pi over 8 is now in quadrant 1, so I can just do arcsine of sine of 3 pi over 8 is 3 pi over 8. So another example. Find the exact value, if any, of each function. Sine of arcsine of 1/2, sine of arcsine of negative 2.5. Now back on a previous slide, back at the beginning here, we had the following. The sine of the arcsine of x is equal to x as long as x is in the domain of the arcsine function. What's the domain of the arcsine function? Negative 1 to 1. So for part A, because 1/2 is in the domain, we just use this property and we say that the sine of the arcsine of 1/2 is 1/2. However, for part B, negative 2.5 is not in the domain of the inverse sine function. So I can't even do it. Okay, so sine of arcsine of negative 2.5 isn't defined because the arcsine of negative 2.5 doesn't exist. Again, remember, if I wrote down the arcsine of negative 2.5 and called this an angle, I'd be saying theta is an angle, and the sine of that angle is negative 2.5. But here's the unit circle, negative 2.5 is all the way down there. There are no angles on the circle that point to something at this height, so this just doesn't exist. Okay, so similarly, we can talk about inverse cosine function, and again, when does the composition of the function with its inverse produce identity? As long as you're in the relevant domain. The domain of arc cosine is negative 1 to 1. The domain of the restricted cosine function was 0 to pi. But if I'm outside that interval, cosine still can produce a value. The regular cosine did not have any restrictions on its domain, so we can kind of finagle our way around it. The bottom one is quite strict. So again, let's find all four of the following. The arc cosine of the cosine of pi over 15, the arc cosine of the cosine of negative 3 pi over 4, the cosine of the arc cosine of negative 0.4, and the cosine of the arc cosine of pi. So I suggest pausing the video and trying to work out each of these. I'll give you a hint. One of them doesn't exist. Two of them are pretty easy. One of them requires a little thought. Okay, so pause here and work it out. Okay, so let's go and check all the solutions. So first for part A, pi over 15 is in the interval that was the domain of the restricted cosine. Okay, so that's in between 0 and pi, which means arc cosine of cosine is just going to be pi over 15. For part B, Negative 0.4 is in the domain of arc cosine, so cosine of arc cosine of negative 0.4 is just negative 0.4. For part C, this one takes a little thought because negative 3 pi over 4 is not in the domain of the restricted cosine function. I can still put it into the cosine function, however, and using even properties of cosine, the cosine of negative 3 pi over 4 is the same as the cosine of 3 pi over 4. And now, what we're doing now is we're saying the arc cosine of negative 3 pi over 4. Forget the arc cosine on the outside, just look at what's inside. Cosine of negative 3 pi over 4 is the same as cosine of 3 pi over 4, and now that's in between 0 and pi. So that's going to be, let me clear out my pen marks, exactly 3 pi over 4. All right, and now part D, you can't take the arc cosine of pi. That would be saying what's an angle whose cosine is pi, and pi is 3 point something. It's way too big to be the cosine of anything. So since arc cosine of pi is not defined, you just can't take the cosine of the arc cosine of pi. It doesn't even exist. Okay, so let's just do a couple more sort of practice problems like this. So for example, what is the arcsine of the sine of 19 pi over 7? So 19 pi over 7 is a weird angle, but it's definitely not in between pi over 2 and negative pi over 2. In fact, 19 pi over 7 is 14 pi over 7 plus 5 pi over 7. Why would I do this? Because that's 2 pi, that's a whole rotation, plus 5 pi over 7. What quadrant is 5 pi over 7 in? It's not immediately obvious, but the real question is, how does it compare to pi over 2? Is 5 pi over 7 bigger than pi over 2, or is 5 pi over 7 less than pi over 2? So how would you figure this out? Cross multiply, and you get what's bigger, 10 pi or 7 pi? 10 pi is bigger. So that tells me 5 pi over 7 is bigger than pi over 2. It's definitely smaller than pi, because 5 over 7 is less than 1. So I am in quadrant 2, because I am bigger than pi over 2, but less than pi. So I'm somewhere in here. So let's just draw it. I'm making no attempt to be at all accurate, except that I know, what quadrant I'm in. So here is my angle, roughly, of 5 pi over 7. But arcsine must be in quadrant 1 or quadrant 4. So what I need to do, let me clear out all of these marks so far and redraw that unit circle a little nicer. Okay, so we know that our angle is somewhere in quadrant 2, like that. Here's 5 pi over 7. Here is a point at the height sine of 5 pi over 7. It's this y coordinate. So I'm actually looking for this angle over here. And again, we're going to do some symmetry arguments. So going all the way to the axis would be 7 pi over 7. It would be pi. Since I've already accomplished 5 pi over 7, this angle right here must be 2 pi over 7. So then I reflect it across, and this angle is exactly 2 pi over 7. In other words, the sine of 5 pi over 7 is this height, which is exactly the same as this height. Therefore, it's the same as the sine of 2 pi over 7. And now I have an angle in quadrant 1. So I can say that the arcsine of the sine of 2 pi over 7 must just be 2 pi over 7. So overall, the arcsine of the sine of 5 pi over 7 is 2 pi over 7. You're just looking for an angle in quadrant 1 that points to the same height. Okay, and let's do another one for arc, let's do an arc tangent. Okay, so what is the tangent of the arc, I think arc tangent wasn't covered in this video. My apologies, we'll do an arc cosine. Pardon me. So what is the arc cosine of the cosine of negative 31 over 25 pi? Okay, totally weird angle. But it's definitely not in between 0 and pi. Well, the first thing we can do is we can use the even-odd properties of cosine, specifically its even, and say, well, that's just going to be the same as 31 over 25 pi. But that's still not in 0 to pi. Okay? So what quadrant is 31 over 25 pi in? Well, since 31 over 25 is bigger than 1, this angle has gone past quadrant 2. Okay? But is 31 pi over 25 bigger than or less than the next quadrant divider of 3 pi over 2? Well, if I cross multiply, you'd be comparing 62 pi versus 75 pi. What's bigger? That one is. So the angle we're looking at now, 31 over 25 times pi, is bigger than pi but less than 3 pi over 2. That puts it somewhere in quadrant 3. So here it is, 31 pi over 25. We're now looking at the cosine of that angle. That's an x-coordinate. So here is the line given by x-coordinate is the cosine of 31 over 25 pi. Okay. So I need to be somewhere in quadrant 1 or 2 to take an arc cosine. That's what the arc cosine will produce is something in quadrant 1 or 2. So I don't want this point down here. I want this point here in the second quadrant. So I need to figure out this angle. Okay? And we can just do a bunch of symmetry arguments. So here's how I do it. Going all the way to the line is pi. What did I add on top of that? So I'm going to erase some stuff. Okay, I'm going to keep the picture up here, but I'm going to erase the work on the side. Okay, so we know what quadrant we're in, so we don't need that work anymore. Great. So the question was, 31 pi over 25, our mystery weird little angle, is pi plus what? So let's call this, I don't know, t. Okay, so pi is 25 pi over 25. So I subtract that over. We get 31 pi over 25 minus 25 pi over 25 is our mystery t. And we get 6 over 25 pi is t. So that is this angle right here. Between this axis and the angle we're actually looking at, that's going to be 6 over 25 pi. So I reflect that, and that tells me this angle here is also 6 over 25 pi. Okay, I'm going to erase the work on the right. Now that we figured out that 6 over 25 pi, we can finally figure out the angle that we're looking for, the dotted line over in quadrant 2. So if the angle between our dotted line and the negative x-axis is 6 pi over 25, well, going all the way to the axis, so let's zoom in on quadrants 1 and 2. Here's our mystery angle that we need to find out, but we know that this angle here is 6 pi over 25. Well, if I call this angle, let's call it theta. If I add theta to 6 pi over 25, I've gone all the way to the negative x-axis, and that's exactly pi. So I'm going to call this, again, 25 pi over 25 to give it a common denominator, and then subtract 6 pi over 25. So theta is 19 pi over 25. So this angle here is 19 pi over 25. And again, I'm going to erase the work on the right. Now that we found that angle, we can basically finish the problem. So what we've now determined is 19 pi over 25 is an angle that has the same cosine that 31 pi over 25 had. So, forget the arc cosine on the outside for a second. Since the cosine of 31 over 25 pi is this x-coordinate, which is the same as the cosine of 19 pi over 25, 19 pi over 25 is in between 0 and pi, so arc cosine and cosine cancel out. And there we have it. The arc cosine of the cosine of negative 31 over 25 times pi is 19 over 25 times pi. There's another way we could have done this problem. Again, let's worry about the, I'm just going straight from here now, okay, from the very beginning. Worry about the arc cosine on the outside later. Once you recognize that this angle of negative 31 over 25 pi is not in quadrant 1 or 2, I'm going to use periodicity of cosine. Forget the fact that cosine is even. Okay, I'm going to use periodicity. So the cosine of negative 31 over 25 pi is the same as negative 31 over 25 pi plus 2 pi. And now I can, so this equals, okay, so I'm just shifting the angle by 2 pi. Well, what's 2 pi in terms of the common denominator 25? So arc cosine of negative 31 over 25 pi. Well, the common denominator will be 25, so instead of 2 pi, I'll call it 50 pi over 25. Inside that innermost term, if I simplify negative 31 pi over 25 plus 50 pi over 25, we get 19 pi over 25. And now I have an angle in between 0 and pi, so the arc cosine and cosine can cancel each other out. So the answer is 19 pi over 25. So there's another way you could have gotten this answer. You can use the even property of cosine and then some symmetry arguments. Okay. Unfortunately, the even property of cosine put us in quadrant 3. Arc cosine is going to produce an angle in quadrant 1 or 2, so once we were in quadrant 3, we had to do some symmetry to get an angle in quadrant 1 or 2 that had the same cosine. As it turns out, we could have also just done a periodicity argument, taken our input of negative 31/25 pi, shifted it forward by 2 pi, and immediately landed in quadrant 2 and been done. Okay, so there's no golden, silver bullet. Sometimes one technique will be easier than the other. They'll both work. So be comfortable with both of them. So in the next video, we'll come back and we'll talk about inverse tangent function.